And so our next speaker is Adnan Hamid from Breker Verification Systems, where he's founder and CTO. Prior to Breker, Adnan spent several years at AMD in Austin, managing the system logic division, working on complex verification solutions. He holds a BSc from Princeton and an MBA from the University of Texas in Austin. And the title of his talk is RISC-V Verification, New Techniques and Approaches for SoC Validation.
Thank you, Meg. How is it I'm the first person at this conference talking about RISC-V? How many people here are working with RISC-V today? How many planning to start a RISC-V project within, say, the next year? Yeah, I think a lot of us will be talking about RISC-V a lot. So my talk is mostly about RISC-V verification. RISC-V opens up, first, for those of you who don't know, it's open source CPU architecture, so you don't have to pay ARM or maybe Intel an architectural license, right? You get to build your own CPU that's compliant to RISC-V. The many vendors building RISC-V cores, there are various open source designs available. So no problem, right? I plug out my ARM core, I plug in my RISC-V core, and I'm good to go. Except not so much, right? ARM puts in billions and billions and billions of cycles of verification. They spend, what was the numbers, like $150 million a year on verification alone. No RISC-V core can do that, right? There's a big concern of this with the RISC-V committee, right? RISC-V International is working on the certification committee, certification steering committee, is it? Which Breker is involved with. How do we help people work out whether they actually understood the specification, which is not easy to understand. And this is just trying to get architectural compliance, right? Not microarchitectural. We're just asking, hey, did you add 1 + 1 = 2 once to prove you know what add means? Not does 1 + 1 = 2 under all conditions. I think there are a number of different challenges that anyone working with RISC-V has to face, right? First, we got to have automated test generation. And what a lot of this talk is about system VIP, something to do automated generation for CPUs, something else to do automated generation for RISC-V-based SoCs. But just automated generation isn't enough. You need extensibility. The whole point of RISC-V is you can add your own instructions, you can pick up your own configuration for RISC-V, and the generators have to be able to match that. And you're going to have different needs. Some cores are going to be embedded cores, very simple pipelines. Others will be high-performance cores, superscalar out of order. You're going to have multi-cores and so on, right? So lots of different problems for different people. One point that I am making in this presentation is folks who design CPUs worry about one set of problems. Folks who design the SoCs that integrate those CPUs worry about a different set of problems, okay? And I have a big list of things to worry about over here. I'll hit them in later slides, so don't worry about trying to read them all here. Now, why does Breker think they have anything to say about this, right? So Breker's core technology that we've been working on for the last 20 years is test suite synthesis. This means from a single source of truth, we can synthesize stimulus, checks, coverage, and debug information. And I'll talk to you a little bit about what we mean by this. And the early start of this work was actually in CPU verification. I was at AMD in the mid-90s. And the strategies I'm talking about today was used to get AMD compliant with Intel on x86. Where x86 is a very, very difficult architecture, and we were doing big superscalar processors. So all that stuff is now coming to RISC-V. Okay, let me talk a little bit about AI, right? Can't have a presentation without AI. Today, AI is synonymous with generative AI, LLMs, deep learning, neural networks. These all come from the same history. Breker ended up being the hipsters of using AI in verification because we started doing it well before anybody else was talking about it. And we did not come down the neural network learning path. We came down the expert system path, right? So learning says there's a huge bunch of data and I'm going to figure out what the patterns are. Expert system says I'm going to create a way for smart human beings to put in information into a system in an efficient manner such that tools can use it. Okay, we came down this. The expert systems, and among expert systems, planning algorithms are one particular approach. So why are we using planning algorithms? If you're not using planning algorithms, you're probably using constrained random. And constrained random is great when your problems are broad and shallow. Throw a bunch of random crap at it, and surely soon enough, you'll find all your bugs. But as somebody said, actually, Andy said to me at lunch, right? Even if you have something as simple as UART, you can't really throw random reads and writes into its registers and expect anything to happen. There's got to be a pattern to how you program, configure the UART, and get it to do something. So this is where planning algorithms come in. What are planning algorithms? They're a class of algorithms that want to start with the objective, something it wants to check. It wants a set of rules about its universe, and it wants the initial state. And what it does on each iteration, is it starts with the thing it wants to check and works backwards through its state space to construct a sequence of stimulus that allows it to check what its check objective is. You guys all listen to me saying, haven't I heard those words before? And you absolutely have, right? This is the principle of how formal works. You have an assertion, you work backwards to your constraints. So these are formal techniques for generating dynamic tests, right? So each time is generating a test case, is coming through a formal flow to generate the test. And this idea becomes very, very powerful because once you learn about planning algorithms, you can chain them together. The prerequisite for one plan can be the objective of the next plan, and so on. And that's what I'm trying to stitch together in this presentation. So when you do this stitching of planning algorithms, you can start to cross a lot of different features to create individual scenarios. So do I get I do get a little thing. Okay. So here's roughly the top level planning structure we have for our core verification. And each of these blue boxes carry under it a graph of its own, right? This is a graph, and each level has a graph under it. And the idea is that we can cross lots of different capabilities. So every time the tool is trying to generate a test case, here's the line of reasoning it goes through, right? It kind of goes, okay, what privilege level do I want to be in? At that privilege level, let me come up with some mess of branches, right? Branches are really important for superscalar out-of-order machines. You're trying to confuse branch prediction. You're trying to confuse what needs to be wiped out of the pipeline. Then each leg of the branch needs to be filled in with a bunch of instructions. So you can, in RISC-V, you can do the compute instructions, right? Register, 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 immediate kind of things. That can get you into saying, okay, generating random instructions, random registers, this is not hard, right? You can do it in 10 lines of code. But hey, how about I put a little bit of thought into the registers I pick? Let me use registers that were recently used. Let me use registers that haven't been used for a while. Let me repeat operations of the same register over and over again. I'm trying to create all the different hazard conditions that can exist between registers. And then having picked a register, sometimes I need to initialize them if they don't have a value. Well, what are interesting ways to create values so that I'm not just doing random, but doing all the corners of different kinds of values. Okay, that's just branches. Then there are load store instructions. Okay, so this is memory operations. Well, a load instruction is not hard to do, but you can do a lot of work in picking interesting addresses that cause hazards, right? So picking addresses that hit on a particular cache index so you get evictions, picking addresses that false share with other addresses you're using so you're getting contention. A lot of AI software likes to access data in particular stride patterns. So model those stride patterns, try to see if hardware breaks, hardware has performance issues, right? These things have shown up in real life. And once you have your physical address, you can run it through your paging system, come up with complicated ways to page map those addresses, complicated ways to go through the PMP, until you're dealing with the physical address. And then finally, one form of branching is to do exceptions, right, or interrupts, either synchronous or asynchronous events that cause the CPU to branch. So what I'm really trying to do over here is show you how a planning tool can go through each of these stages of reasoning for one scenario and cross together many different capabilities. And this proves to be a very powerful way to test all the corners of a CPU implementation. Down here at the bottom, in a picture that is completely Greeked and out of focus, is a view of how you can think about coverage of these scenarios. If you consider that each of the blue boxes in my picture have a graph under it, now we can start to ask the question, have we exercised every path in the graph, right? Many of these graphs are reconvergent, and you can come up with some picture that basically unrolls the graph into a tree, and you can start asking, okay, which paths are reachable? Of the paths that are reachable, which have been covered? And it turns out that you can not only do the scenario coverage, you can say at this point you have enough information to say, oh, let me figure out which paths have not been exercised yet and do automated coverage closure simply based on the knowledge we have. Another piece of this technology is schedule solving. 10 minutes? Okay. You'll give me a 5-minute too? Another part of this technology is schedule solve, and we're going to talk about that, especially as we get into multi-cores, right? So let's say you have some scenario I have over here for a little camera subsystem where maybe to take a picture, a camera captures an image, encodes it, writes it to the SD card. Maybe to look at a picture, we read the card, decode it, display it, and so on. If we have only one thread to work with, we can create one scenario and then schedule another scenario. But if you're dealing with multiple threads, you schedule a scenario, interleave another scenario, interleave, 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 and pretty soon you have a complex test cases. These schedules are resource aware, so you never see the SD card controller being used on two threads at the same time. The scheduler knows that there's a hardware resource being used. Similarly, we can schedule memory for these operations. We can say, hey, maybe the first scenario uses a couple of buffers in memory, and the next scenario has a high propensity to reuse some or all of those addresses. So you're trying to create interesting address conflicts. So what am I about really over here? I'm talking about, hey, not only do we need a planning algorithm, we need it to sit on top of schedule planning and memory schedule planning so that we can create interesting cases. So over here, we have a rough outline of the kind of things you'd want to do if you're doing CPU verification. And I'm not going to read through all of them, but any of you who are familiar with CPU verification, yeah, we do the basic instructions, but that load store is usually 80% of a design. Dealing with branches and exceptions becomes a big hassle. Then we go into our privilege levels and our paging and so on. So this is listing some of the challenges that we're addressing with the system VIP. It is really hard to do slides that are exciting to look at that show tests. We try. But, so we're showing over here some random instruction generation. Random instruction generation, I think, is pretty darn easy. But coming up with interesting ways to pick those registers, coming up with interesting ways to initialize those registers, putting those instructions into a rat's nest of branches, these are things that planning algorithms can do that maybe are hard to do with other strategies. I talked a little bit about a coverage in my first slide, so here's what it looks like, right? You might run a few tests and might say, okay, I've done 27 out of 103 of the reachable cases, and you can dig down into the data and it'll tell you which ones are not reachable, the white nodes, versus which ones have not yet been reached, the red nodes. Most CPU designers consider load store to be 80% of the design, right? It's the hardest part. So coming up with load and store instructions, not so hard. Coming up with interesting addresses to do the loads and stores to and external snoops to is much more interesting. And that is yet another stage in the planning algorithm that we go through. So if you see over here, we're doing a series of writes, but if you actually study those addresses, the addresses are not random. They're designed to step on each other. And basically, your trying to write part of a cache line, and right behind it, you're trying to overwrite part of that cache line and the next cache line or something like that. Okay. Exceptions are often hard to test because the asynchronous, if they're traps due to external interrupts, they are asynchronous. If they're due to fault, they are synchronous. But you got to have all the infrastructure in place to generate the interrupt, make sure you've seen it, and come back and continue execution. So we do all of that. Paging. Every CPU's got to have paging. Well, every CPU that wants to run Linux has got to have paging. And it's complicated. And the hypervisor mode, the hypervisor extension, makes it even more complicated because you're looking at two nested layers of paging. And again, these planning algorithms are excellent at figuring out, okay, they start with the premise, I want to come up with a virtual address for this physical address, and they can come up with some crazy page map to decide how that should be mapped. And this has been powerful. This has been finding a lot of bugs. I talked to you a little bit about scheduling. Often we're in the business of testing clusters of CPUs. The tool can put multiple software threads on each CPU, so you can get a lot of concurrent testing going. Okay, but that's not enough. That's not enough. All of that together is basically covering what is in the ratified specification for RISC-V. But anybody who's doing RISC-V is invariably doing something custom, a custom instruction, a custom something. So we've made this whole flow super easy to extend. So it takes 10 lines to add your own instruction. Okay. So moving forward from CPUs to SoCs, right? Different set of concerns. Over here, we are much more worried about memory management, about caching, about memory ordering, about atomics, all these multi-core things. And here's kind of the overview architecture of how we think about system level test generation. Over here, we're trying to say, okay, this picture is drawn going this way, the other picture was drawn going the other way. Planning algorithm doesn't care, but we're picking one of multiple possible multi-agent scheduling patterns. We're picking good addresses to do them with. We're deciding which system agents should be playing. We should decide what kind of operations we're doing. Again, it comes back to the point of we can cross many verification concerns within each scenario. Going through some examples, multi-core coherency is always popular. The tool can generate tests where it's intentionally trying to create various cache lines transitions and making sure that they all work. Atomics is always a big concern when you're doing multi-core. So we have tests that will make sure that the multiple operations are working on the same true shared memory, and we're making sure the result is the aggregate of all those operations. Memory ordering is always a big thing. So Decker is one version. There's a set of litmus tests that we're now crossing with all our memory operations. And then there are these so-called false share or memory slicing tests, where what we're doing is we're taking a set of cache lines, slicing them up into slices, if you will, handing each slice to a different agent and having each agent just rotate on their set of addresses. And what you're doing is you're trying to get one agent is working on the first slice, the second agent on the second slice, and so on. And they're all competing for the same set of cache lines. Now you do interesting things on how you pick those cache lines. Maybe you pick them all to go to the same set index. And you got some complicated tests going on where everybody's competing for the same cache lines that are continuously evicting things from caches. Hard for hardware. Okay. So wrapping up over here, these strategies are proving to be very, very successful. We have some short list of bugs that have come out of over here. There are many more interesting bugs that are dropping out, both in, we're doing work with some open source designs. So there have been like 4 or 5 bugs that have fallen out of Wally. We're just starting working on the CVA6 design. We're finding bugs in commercial designs. So it's generally being very, very effective. Okay, with that, I'll open it up for questions.
Time for one question, if there's one from the audience. There is one online. Let me quickly grab the online question.
That was so clear, nobody had questions, huh?
Yeah, so why AI? How can AI generate more active stimulus?
How can AI generate more active stimulus? Oh dear, I could give an entire lecture on this point. I think the point over here is to get AI to generate more active stimulus, but we are using expert systems where we've told the AI how to get to various checks, and it ends up with a huge search space and is traversing as many of those paths as it can in the available simulation time.
Okay, I think we'll finish there. We'll move to our next speaker. Thanks, Adnan. Thank you.